All right, we have learned about chirality, have learned about enantiomers. You have drilled some enantiomers right here, right? Now the next question is, are all molecules chiral? No, not all molecules chiral. You have seen it before. All right, so are these chiral molecules? Not really. If I reflect it into the mirror, acetic acid and its mirror image line up perfectly, right? Benzene, same thing, line up perfectly with its mirror image. Vanillin, this compound that smells like vanilla, same thing. This guy's flat, right? Line up perfectly with its mirror image. Capsaicin, the compound that put on your tongue that give you the hot burning feeling, same thing. Line up perfectly with its mirror image. Not all molecules are chiral. Yeah, not all molecules have the enantiomer. Only chiral compound can have enantiomers. All right. Now the question is, how do we know if a compound chiral? Here is the characteristic of a chiral compound. Okay. Now chiral molecules have this. Number one, possess a chiral center or stereocenter, at least one. Right. Give you some example. What is chiral center? A carbon that has 4 different substituents. Doesn't have to be carbon, but most of the time it's carbon, right? So a carbon that has 4 different substituents. I'll take a look at this carbon right here. This is the chiral center, okay? So what do you mean by 4 different substituents? This carbon right here got an OH, that's 1. A propyl group, that's 2. A methyl group, that's 3. What's the other one? The hydrogen, point to the back, okay? That's 4. 4 different substituents on it, right? The following don't have chiral center. For example, this carbon right here, OH is 1, ethyl is 2, ethyl, not different substituent. Gonna be 4 and different substituent. This is 4, of course, got hydrogen too, but these ethyl group are the same. So that doesn't count, right? This carbon right here got 2 hydrogen on it, so that's not chiral center. So first off, a compound, a molecule will be a chiral. 1, need to possess at least 1 chiral center. What is chiral center? 4 different substituents. Okay. And have no plane of symmetry. We're gonna talk about spend time a little bit time on a plane of symmetry later, okay? But also have no plane of symmetry. Look at this guy. So this guy right here got 2 chiral center, 4 different substituents, and doesn't have plane of symmetry. If I have Tusky look through molecule from that direction, he's gonna see like this. On his right hand, OH point up, right there. On his left hand, OH point down. So OH point down, look like that. Equatorial right here. All right. So they don't have plane of symmetry. On the other one, this guy right here, this is plane of symmetry. All right, I'm gonna have Tusky look through bond like that. So 2 chiral center, but this guy have plane of symmetry. That in the middle right there, that's a plane of symmetry. Imagine let's say like an imaginary line. A plane of symmetry. A plane of symmetry show that on the left side and the right side look the same, basically. Okay, this one doesn't look the same. If I have an imaginary line like this, OH point up, OH point down, they don't look the same. But this one totally OH point up, OH point up. All right, that's the plane of symmetry. All right, a molecule would be chiral. 1, need to possess 1 chiral center, 4 different substituents, and 2, have no plane of symmetry. Okay, all right. Let's take a look why the having 4 different a chiral center matters. Why having no plane of symmetry matters. I'll take a look. Okay, so this guy right here, this is a chiral compound. 4 different substituents right here. It's got chiral center there. If you reflect it into the mirror, this guy point up, in the mirror point down. They cannot line. And I twist it 180 degrees. You can line them up. That's an enantiomer. If they line up perfectly, that's not an enantiomer. This guy's a chiral, right? But this is I show you totally. This guy got a chiral centers, right? So it's enantiomer cannot line up perfectly. Now this guy right here, no chiral center. This carbon right here doesn't have chiral center. Yeah, 2 same substituent, you know. If I reflect this into the mirror, take a look. All right, and now I'm gonna spin it 180 degrees. Look just like the original compound or original molecule. Okay, this is a chiral. That's why having chiral center matters. All right. Now let's take a look at the effect of plane of symmetry. This guy here, 2 chiral centers, but this guy got plane of symmetry in the middle. You know, left side, right side look the same. So 2 chiral center, but plane of symmetry made this guy a chiral. Look at it, it's mirror image. So that's its mirror image, right? So the guy up, this guy go down, down. Now I'm going to spin 180 degrees. Look exactly the same. That's the effect of having plane of symmetry, right? Make a molecule that's supposed to be chiral a chiral. And last one, this guy right here. So this is a chiral compound, two chiral centers, no plane of symmetry, right? This guy doesn't have plane of symmetry. I reflect it up, down. You're gonna get down and up, right? Now I'm gonna line them up. I'm gonna turn it real quick. So turn, spin 180 degrees. Look exactly the same. Now line them up. Nope, doesn't line up perfectly. So that this guy point up, OH point down. You can't line them up, right? So again, a molecule will be chiral. One, chiral center, right? Which is 4 different substituents, and 2, no plane of symmetry. Let's do some practice together right here on the next video.